Okay. In the last lecture, right at the end, I was telling you that there was a theoretical physicist by the name of Erwin Huckel who found that if you have a cyclic arrangement of p orbitals and that they are distributed on a molecular framework that is flat, and if the number of electrons corresponds to 4n plus 2, where n is a whole number, then the substance will be aromatic. And by saying that it's aromatic, I mean that it will be especially stable. And of course, the most famous example of this rule is the compound that is called benzene, and for which we can write two resonance structures. I have written just one. And if you look at that Lewis structure that I've written, you will see that there are 6 p orbitals and 6 p electrons distributed over a cyclic framework, a regular hexagon, and 6, if you put 6 equal to 4n plus 2, then n equals a whole number, which is 1. Because 4 times 1 plus 2 equals 6. And that molecule is flat. So it satisfies the Huckel rule, the 4n plus 2 rule, and it's flat. Therefore it is aromatic. Well, we knew it was aromatic because this is the prototypical aromatic compound. It's a compound that clearly is more stable than it would be, than you would expect if this were a double bond and that a double bond and that a double bond. Because I told you about an experiment where you took cyclohexene and hydrogenated it to get some heat out. Well, if you've got 3 enes in a 6-membered ring here and you hydrogenate this, you'd also get some heat out. And if it wasn't especially stable, you'd get out 3 times the amount of heat that you get out from 1 mole of cyclohexene. But this is a lot more stable. It's 36 kilocalories per mole more stable than that. The reason is you can write resonance structures. There's something special about the delocalization of electron density over a cyclic flat arrangement when the number of electrons satisfies 4n plus 2, where n is a small number, a whole number. If you have a bigger ring, then again, if it is flat, and if the number of electrons satisfies 4n plus 2, the compound will be aromatic. And so here is another example. And this is a substance called 14 annuline. And there are 14 atoms in that ring. And there's 1, 2, 3, 4, 5, 6, 7. So there are 7 double bonds. So there are 14 p orbitals. The thing is flat. 14, you put 14 equal to 4n plus 2, 12 equals 4n, and so n equals 12 over 4, which clearly is 3. So this stuff you would expect to be aromatic, and indeed it is aromatic. But if you make other compounds which are not flat, or for which when you put 4n plus 2, when you try that equation, n is not a whole number, or negative, or something strange, it's not aromatic. Now, what I've told you so far is if you've got a flat species and it's cyclic and the number of delocalized p electron satisfies 4n plus 2, the stuff is aromatic, which means it's especially stable. I've only shown you a couple of examples, benzene and that 14-annuline, and those two examples are neutral molecules. But supposing I take this, cyclopentadiene, which is a molecule you probably met in the lab, or heard about. And if I treat it with a strong base, this material, which is negatively charged, has 6 electrons in p orbitals on a flat skeleton, and it's cyclic. And 6, as you know from the case of benzene, satisfies this Hooker rule for n plus 2, n is equal to 1. So here I have a negatively charged species that is also aromatic. Now you know from last term's chemistry that a simple hydrocarbon does not have acidic hydrogen. But this thing does have acidic hydrogens. Why? Because if you break this bond and put the electrons onto that carbon, you get an aromatic species, so it's going way downhill. So it's especially easy to remove one of these hydrogens. So cyclopentadiene has an abnormally acidic hydrogen, because what's formed is aromatic. So I've told you now an example, I've given you examples of the Hooker rule for n plus 2, for neutral molecules, and now for a negatively charged species. And if you draw an orbital picture for this stuff, there are 6 electrons, and you remember this donut description that I told you last time, and I pretended I never knew what goes on in Tim Hortons and stuff like that with the so-called edibles that they provide. It's the same sort of picture here. And of course, once again, you don't have the 6 electrons all in one orbital. The orbitals come in various energy levels, and we feed in 2 into the lowest, 2 into the next, so forth and so on. You don't have to worry about that. I just want you to know that you can have negatively charged species that are aromatic. And of course, immediate, since I told you neutral species, negatively charged species, the immediate question that jumps into your mind immediately is, can you have positively charged species? And the answer is yes. You can get a framework that's flat, that's got p orbitals on adjacent carbons, such that the number of electrons in the p orbital satisfies Hooker's equation, then the stuff will be aromatic. Now let me just see if I can clean the board. No.
Use the paper towel. To write it on it though. Yeah, kind of. Maybe in another color. That's what he's doing. Nope, he's going all the way around.
You can make a positively charged ion like that, and it will be aromatic. First of all, it's flat. Secondly, it has p orbitals on every single carbon. This one, as I've drawn it here, is empty. But there are 6 electrons, and so you can get this donut shape, overlap of the top lobes of the p orbitals on the one side, and the bottom lobes of the p orbitals on the other side. So you've got a donut of overlapping p orbitals on top and bottom. 6 electrons, it satisfies the Hooke rule. So you can sorry, was somebody saying something? Okay, I heard some noise on this microphone. Now, there's one other complication, or one other extension. I've given you the rule 4n plus 2. I've given you examples of neutral molecules. I've given you one example of a negatively charged species, and I've given you one example of a positively charged species. All of these have to be flat. They all have to have the p orbitals on adjacent carbons. All of these examples I've given you are monocyclic. There is only one ring. So the next question is, can you have aromatic compounds in which there is more than one ring? The answer is certainly yes. Can those of you at the back see this red on this dirty board? Yes. Good. I hope that the next person who uses this room isn't as kindly and gentlemanly as I am and goes absolutely berserk and phones up the president of the university to get the criminal who started messing up the board dealt with. This compound is called naphthalene. It is flat. If you count up the number of p orbitals and the number of electrons, there's 2 here, 2 there, 2 there, that's 6, 7, 8. 2, 4, 6, 8, 10, sorry. That's better. So n equals 2. So it satisfies the Hooke rule. Now, if it works with 2 rings, will it work with 3 rings? And obviously the answer is yes, it will, because 2, 4, 6, 8, 10, 12, 14, 4n plus 2 equals 14. Therefore, n equals 12 over 4, which is equal to 3. So you can have multi-ring compounds, and here are just a couple of examples. So remember, the molecule must be flat. The number of electrons in the p orbitals must be equal to 4n plus 2, where n is a whole number. So it's 1, 2, 3, or 4. You can't have n equals 0 because that's just ethylene, and ethylene's not aromatic. But for n equals 1, it's benzene, n equals 2, n equals 3, and so on. Must satisfy that, and it must be a cyclic array, and you all have cyclic. In other words, by a cyclic array, I mean the p orbitals must be on the perimeter of a cyclic framework. Here, you see, if you watch my hand, I'm going around a cyclic framework, and in every one of these corners, there's a p orbital. So that's what you need. That's a good test for aromaticity. Okay, now, I've done enough about that. I'd like you to do, for your homework, a few problems. Let's see if I can...
just look like cleaning stuff.
Have to?
Yeah.
What about you?
I haven't done them yet.
I did NMR.
Okay. The stage that we've reached now in what I've taught you about aromatic compounds can be summarized in a minute or two as follows. In the early development of organic chemistry, there were some compounds that had a characteristic, fairly pleasant smell. A typical example would be cinnamaldehyde, and many other examples. It was eventually realized that they all contain a particular structural unit, the so-called benzene ring. Benzene itself is the prototype of this structure because the compounds have a nice smell, we call them aromatic. But now a compound doesn't have to have a nice smell to be called aromatic. It has to have certain characteristics. The most famous example of aromatic compounds is benzene. If you try to draw the structure of benzene using what are called Lewis structures, that's these lines. You use one line to represent 2 electrons shared between 2 atoms, 2 lines to represent 4 electrons shared between 2 atoms in the special way of a pi bond, which you dealt with last time. If you try to use such a structure and you interpret it strictly according to the meaning of a single line and double line, you draw the wrong conclusion. You'd think that benzene had alternating double and single bonds, but it certainly doesn't. You simply cannot draw, using these line structures, a proper picture of benzene. What you can do, however, is to draw a regular hexagon of the correct dimensions of benzene, and it's known from various data that all of the bonds in benzene have the same length, neither the length of double nor the length of a single bond, but somewhere in between. What you can do is to, in the case of benzene, draw 2 of these line structures, and you realize that neither of them is correct. They're all imaginary structures, and we say that the actual structure of benzene is somewhere in between, and another way of saying that is that benzene is a resonance hybrid of the various structures that you can draw. And it's very convenient to draw just one of the 2 possible structures, as you will see in a few moments. So that's the resonance idea of benzene. It's a very strange sort of thing. It's like going to the zoo and seeing an animal that you can't really describe except by saying it seems that its mother was some hypothetical creature, perhaps a unicorn, and its father was another hypothetical creature, a dragon. So it's very strange, but it turns out to be very, very useful. And when you can write resonance structures for a compound, what it means is, among the things that it means is that it's a lot more stable than it would be if you couldn't write resonance structures. There is another view of the characteristic of aromatic compounds, and that is that you can write down a so-called molecular orbital. You can take all the p orbitals on the correct framework and you allow them to overlap. And if you do that, if you combine 6 p orbitals, you'll get 6 molecular orbitals. They're at different energy levels, and you imagine that electrons are fed in 2 into the lowest level, 2 into the next level, 2 into the next level, and so on. Another picture is, you can just imagine the p orbitals overlapping above and below the ring like 2 donuts. And then there's a further concept, and that is this Huckel rule, which says that if the carbon framework is planar, and if you've got p orbitals on on adjacent carbons, whether they're full or empty, doesn't matter, provided that the number of p orbitals satisfies 4n plus 2, where n comes out to be a whole number. In such a case, then the substance will be aromatic. The pictures that you draw using these lines won't represent the true structure. You'll be able to draw resonance structures, and the compound will be more stable than if you couldn't draw resonance structures. So that's the theoretical background of these aromatic compounds. Now, these aromatic compounds turn out to be tremendously important, and one of the reasons is that they undergo a number of useful reactions that give us things that are very useful to us. Now, what are these reactions? Well, as I've told you, if you draw a typical single resonance structure, this does not mean that there are true double bonds in there, and it doesn't mean that there are true single bonds. And the chemical properties of this stuff, which is benzene, are different from what you would expect if there were true double bonds and true single bonds. And in general, if you treat such a substance with another compound, which is an electrophile, and I'll give you plenty of examples in a moment as to what an electrophile is, you will find that what you get is a reaction that I can write like that. So what has happened if you treat benzene with one of these electrophilic reagents? What has happened is one of the hydrogens on benzene, and it doesn't matter which one because on benzene itself they're all absolutely identical, one of the hydrogens has been replaced by this group E. Now what can this group E be? Well, let us if you take chlorine and ferric chloride, you get something, and I'll tell you shortly what it is, that corresponds to this. But the outcome is that you get chlorobenzene. And if you take nitric acid and sulfuric acid, you get nitrobenzene. So this process is called nitration. And this process is called chlorination. And if you, I'm going to draw it over here, if you take very strong sulfuric acid, this is sulfonation. And if you take an appropriate alkyl halide with aluminium trichloride, you get an alkyl group attached. And this is called Friedel-Crafts alkylation. And there's one other. I don't know if I've got space, so let's clean some board here if I can. And this is Friedel Crafts acylation. So, what you can see from this very brief summary, you have a question, good.
Does that say fuming?
Fuming, yes. F-U-M-I-N-G. Fuming. If you take ordinary concentrated sulfuric acid and you bubble sulfur trioxide into it, you get something called fuming sulfuric acid. If you take the stopper off the bottle, these white fumes come out. It's sulfuric acid with an extremely low water content. It's pretty aggressive stuff. I wouldn't recommend washing in it. So this is just a summary without any explanation. All that you can really understand from this is that if you take benzene itself and treat it with various reagents, one of the hydrogens is replaced by some group. The group could be an alkyl group or an acyl group. An acyl group is just a carbonyl joined to another carbon. Or it could be a nitro group, or it could be a sulfonic acid group, SO3H, or it could be a halogen, chlorine or bromine. Or it could be an alkyl group. So you can do various things to benzene. Now in all of these very simple examples, I've replaced one of the hydrogens on benzene by these groups. So there are a few questions that should have jumped into your minds. One is, what's going on here? How does all this happen? But then another one is, so he's replaced one hydrogen in every case. Could he replace another hydrogen? The answer turns out to be yes. But then there's a big complication. If you replace a second hydrogen, not all the hydrogens on the ring are the same. You see, in benzene, all 6 hydrogens are the same. But once you've got one substituent on benzene, they're not the same. 2 of the hydrogens are ortho to the substituent, 2 of the hydrogens are meta to the substituent, and 1 of the hydrogens is para to the substituent. So now, when you introduce a second group, there's the question, where will this second group go? And there's an even more subtle question. If the rate of the reaction when you introduce the first substituent is some value, once that substituent is in, will the rate of the next reaction, putting in a second substituent, be higher or lower? If it's higher, you're in trouble. Because as soon as one substituent goes in, the other one will go in just as well, so you get a mixture. So there are all sorts of complications, but before I deal with that, what I need to do is to explain to you how this happens, because it isn't magic. It's nicely understood, and it's actually very easy to understand, and when I explain it to you, you will realize why it's so convenient to use one resonance structure, either this one or the other one, and why it's more convenient to use this type of picture than an alternative, which I have mentioned before but not used very much, which is just to put a circle in the 6-membered ring. And a circle in the 6-membered ring is a very quick shorthand way of saying that you've got 6 electrons delocalized over the perimeter of the ring. But that picture is not nearly as useful as the one in which you draw one of the resonance structures. So now if I'm able to clean the board, seems to be working okay. Right, now I can tell you how these reactions actually go. What happens is that the electrons from the benzene ring attack one end of this electrophilic reagent. An electrophilic reagent is simply a reagent that likes to be attacked by electrons. And I told you last time, an Anglophile, somebody who likes England, a bibliophile, somebody who likes books, and an electrophile is an entity that likes to be attacked by electrons. And so electrons from the benzene ring attack the group E, and if E forms a bond with carbon, as I've shown, then unless E can expand its valency, which normally it can't, it has to lose a bond, and so the group A departs with a pair of electrons. So the valency of the atom represented by E remains constant, which is a normal situation. Now, it's not helpful for us to ask from which orbital are the electrons coming. They're actually coming from the highest occupied orbital, but we don't need to do that. In order to understand what's going on, we temporarily pretend that this is a double bond. And if you do that, it's exactly the same as what you had last term when somebody did this. And then that was captured. But here, that second step doesn't take place. The electrons come out here, as one of my students once said when he was just beginning, said, they leap out. That's what they do. They leap out. And so you get a species like this, for which I can write some resonance structures, because I could take these electrons, move them there, I get a plus charge here. I could take these electrons and move them there then, get a plus charge here. So I can write some resonance structures. So this is a stabilized, positively charged species, but it is not as stabilized as benzene. Now this species, if you asked it what could it do, it would say, oh, I could stay like I am. Or it could say, I would like to be attacked by A minus over here, which means it would no longer be aromatic. Or it could do something else. It could re-aromatize in this way. Now, the whole thrust of what I'm telling you in today's lecture and in the previous day's lecture is that a benzene ring, which is the prototype aromatic compound, is especially stable. And if some molecule or some species that's higher in energy than a benzene ring can aromatize and become an aromatic substance, that's what it would prefer to do. So unlike the case of an ordinary double bond where the carbocation is captured by attack by the nucleophile, this carbocation is not captured by the nucleophile. Instead, by the negative charge species, instead, the negative charge species removes a proton so that the whole system is re-aromatized. So that's how you can replace one of the benzene ring hydrogens by this group E. The electrons leap out of the benzene ring. We imagine that it comes out of one of the double bonds, doesn't matter which one. to give you a resonance stabilized intermediate that is less stable than benzene, and that prefers to re-aromatize by loss of a proton, so that you now end up having replaced one of the benzene ring hydrogens by this group E. So there are at least two steps in this process. First, the electrons leap out onto the electrophile, give you a resonance stabilized carbocation, and then that is aromatized by loss of a proton. The net result being that one of the benzene ring hydrogens is replaced by this group X. So that's the general approach for all these reactions. I showed you an example of chlorination, I showed you an example of alkylation, acylation, nitration, sulfonation. There are a few others, but those are the main ones. And in every case, this is the basic mechanism, with a few little twists here and there, depending on the individual case. So what I want to do now is to go through in more detail these individual examples. How do you convert benzene to bromobenzene? Then how do you convert benzene to nitrobenzene? Then how do you convert benzene to benzene sulfonic acid? How do you convert benzene to acyl benzene, Sweden-Krebs acylation, and so on. And you will see that they all conform to this pattern, but each one has one or two little features that are characteristic for it. A lot of this mechanistic work was worked out in a place called University College London. And when I was an undergraduate, when I wanted to become an undergraduate, I was a schoolboy, I applied to University College London. And they rejected me. They rejected me because I gave a stupid answer to one of the questions in the oral exam. They asked me where the noble gases had been discovered. I gave the wrong answer. I mentioned some other university, and they said, no, it was discovered in the lab next door. So they sent me a letter saying, unfortunately, they couldn't offer me a place in the Bachelor of Science course. But then, a year later, you have to take public exams. So I applied to Imperial College, which was actually much better. I didn't know that, because it was full of Nobel Prize winners. But when the results of my public exams came out, I got a letter for them saying that they could indeed offer me a place. I felt like giving them a very short answer, but I didn't. So I went to Imperial College, but whenever you're asked a question, where was something discovered, and you're at some place being interviewed, if you don't know, the best guess says, I suspect it was discovered here. Then you won't get the letter of rejection. Okay, now a lot of this was done at University College London by a man called Inglow, a very famous mechanistic chemist. Let me tell you about halogenation. If you take benzene and mix it with chlorine in the dark, nothing happens. But if you add ferric chloride, then you get a very nice yield of chlorobenzene. And if you use bromine and ferric bromide, you get a very nice yield of bromobenzene. Now, by the way, before I continue, I should explain to you, why are people interested in chlorobenzene, bromobenzene, nitrobenzene, benzene sulfonic acid, alkyl benzenes, acyl benzenes, and so on? And the reason is that once you've got one of these groups on, there are all sorts of other things that you can do to make loads and loads of different compounds, some of which are very helpful, many of which are very helpful to us. So what's going on here to account for the fact that you must have ferric chloride or ferric bromide? Well, let's do the bromine business. you get some complex form. And that complex is now more electrophilic than bromine itself. And so that's what happens. And that thing now decomposes. So let me write it again over here. What did I write there? I put the bromine here. It doesn't matter, but I just want to make it easy for you. So you can see that the ferric bromide is a catalyst. To use a small amount of ferric bromide, a stoichiometric amount of bromine, that just means the amount of bromine that you need according to the equation. So for 1 mole of benzene, you need 1 mole of bromine. And probably you'd add 1/10 of a mole of ferric bromide. And if you do that, the ferric bromide reacts or combines with the bromine to make something that is more electrophilic than bromine itself. And then the electrons in the benzene attack that new species to give you this resonance stabilized species, which, as I indicated before, can aromatize by losing a proton. And so you end up with bromobenzene. And if you do it properly, you'll get a very good yield of bromobenzene. Now exactly the same situation applies to chlorine. You take chlorine and you mix it with ferric chloride. And exactly the same thing happens and you end up with chlorobenzene. Now you may wonder, why haven't I mentioned fluorobenzene and why haven't I mentioned iodobenzene? Well, there's a very good reason. Fluorine is exceedingly reactive, and in order to do a fluorination, you need special apparatus and special techniques. And because it is so reactive, very frequently fluorination of organic compounds directly with elemental fluorine does not go well. So much heat is given out that the molecules smash to pieces. So fluorination is a subject by itself. You can make fluorobenzene, you make it a different way, which I will eventually show you. What about, why haven't I told you about iodobenzene? You can do the reaction with chlorine, you can do the reaction with bromine, why can't you do it with iodine? Well, it turns out that iodine is not reactive enough. And so you can do an iodination, but it's under rather special conditions. So this so-called aromatic halogenation, for all practical purposes, is limited to chlorination and bromination. And in the next lecture, I will talk about the other examples of electrophilic aromatization.